Dr. Y. Sarada, Professor, Department of Mathematics, Anna University. Her area of specialization is applied probability and stochastic modeling. She has about 25 research publications in national and international journals. She has guided students for research projects. She has delivered lectures in her area of specialization in many institutions.
Welcome to the UGC lecture series on queuing and reliability. Presently, we are looking into queuing theory. We have just got started with the Markovian queuing models. As a recap, we will just see what we have done so far. We just looked into the generalized Poisson queuing model, where we said that the arrival rates and the departure rates are dependent on the state, namely the number of customers present in the system. For example, probability of no arrival and no departure in the interval of length h units of time is given by 1 minus lambda h plus mu h plus order of h. Suppose you take it conditioned on n present at time t, then the probability would be 1 minus of lambda n plus mu n into h plus order of h. Next, we saw that probability of 0 arrivals and no death or departure in t to t plus h, given that n are there in the system at time t, is given by 1 minus lambda n plus mu n into h plus order of h. Similarly, we have probability of 1 arrival and 0 departure in t to t plus h to be given by lambda h plus O of h. Similarly, p of 1 arrival and no departure in t to t plus h, but condition that there are n minus 1 customers at time t, is given by lambda n minus 1 into h plus order of h. And when there are more than one arrival or departure to happen into the system, then we have the following probabilities. Probability of k arrivals and 0 departures in t to t plus h is given by O of h, that corresponds to the probability of k arrivals in h units of time, and this 1 minus mu h plus order of h corresponds to no departure in h units of time. But since we said due to regularity, product of O of h with 1 or mu h or O of h will give us the expression O of h. So, we have the probability of k arrivals and 0 departures in t to t plus h to be given by O of h. Suppose I condition this with n customers or n plus 1, accordingly the rates will depend on the index, namely you will have n or n minus 1 or n plus 1, whatever is applicable. Similarly, next we have probability of 0 arrival and k departures in t to t plus h to be given by 1 minus lambda h plus O of h. This corresponds to probability of 0 arrivals and k departures corresponds to O of h. All this is happening in h units of time. So, we have the stationarity, the probability depending on the length of the interval, which is h. Once again, as we said before, the product of O of h with the 1 or h or O of h again will give us the result to be probability to be O of h. Same thing we are summarizing with the knowledge that at time t there are n plus 1 customers in the system. The probability of 0 arrival, 1 departure in t to t plus h is given by mu n plus 1 into h plus order of h. Now, we have written the differential, essentially here difference equations. So, p n of t plus h, we wrote it as p n of t into 1 minus of lambda n plus mu n into h plus order of h, plus when there are n minus 1 in the system, probability of 1 arrival in h units of time is given by lambda n minus 1 into h plus order of h, and then more than 1 arrival is given by, that is when there are n minus k in the system, we need k arrivals to take the count to n. So, this probability is given by summation over k equal to 2 to n p n minus k of t into O of h. Next term we have corresponding to when there are n plus 1 customers in the system at time t, which is given by Pn plus 1 of t, into probability of a departure, which is given by mu n plus 1 into h plus O of h. Now we have another term when there are n plus k in the system at time t, k departures should take the count to n. So that is given by this last term, sigma k equal to 2 to n p n plus k of t into order of h. So all this summarized, and we take both the sides limit as h going to 0 and divide by h on both sides. We got these differential difference equations. This is the case when n equal to 1, 2, 3 etc. Similarly, we went on to write the difference equations first in the case when n equal to 0 separately. Here we started with p naught of t plus h, which is equal to p naught of t into 1 minus lambda naught h plus O of h into p naught of t, because at time t no count in the system. In t to t plus h also there should not be any arrival, any departure. That probability was given by the first term, and it is possible that by time t there is one customer and this customer has to depart in h units of time. So this probability is given by p1 of t into mu 1 h plus O of h. Now as before, we took the limit h going to 0 on both sides, divided both sides by h. So we got this differential difference equation, namely p naught dash of t equal to minus lambda naught p naught of t plus mu 1 into p 1 of t. This is the differential difference equation when n equal to 0. So we said we need the initial conditions to solve. We got the initial condition as p naught of 0 equal to 1 and p n of 0 is 0 for every other value which is not equal to 0. And in the steady state we need the probability of finding n customers in the system. So for which we said let us take limit t tending to infinity of p n of t, which is p n, and once we get p n, which is supposed to be a constant, when you differentiate that again in the steady state you will get 0. So we have this quantity limit t tending to infinity d p n of t by dt equal to 0. The same thing, the notation is changed here. d p n of t by dt is written as p n dash of t. So all this is valid for n equal to 0, 1, 2, 3 and so on. Now we said at this stage we got the balance equations, namely the expected rate of inflow is equal to the expected rate of outflow. But what is this inflow outflow to the state n? So we went on to see these equations, namely in the case when n equal to 0, we have lambda 1 p naught equal to mu 1 p 1. You see that this is the case when n equal to 0. When in state 0, out of state 0, how do you come out? By an arrival. When in state to reach state 1, it is possible there is one customer in the system and you get the system to be n equal to size to be n equal to 0 by a departure. So that is what is given by the right hand side here. Similarly, we have the balance equations when n is not equal to 0, namely 1 or 2 or 3 and so on. So we have lambda n plus mu n into p n is equal to lambda n minus 1 into p n minus 1 plus mu n plus 1 into p n plus 1. So we went on to see the simplification of these balance equations to obtain p n as given here. Namely, p n is always equal to lambda naught, lambda 1 and so on, lambda n minus 1 divided by mu 1, mu 2 and so on mu n into p naught. You must observe here that the numerator has n terms because the indices start from 0 and ends with n minus 1 in the numerator, which calls for n terms there. Similarly, in the denominator you have the count index starts from 1 mu 1 and ends with mu n. So again you have product of n numbers here, and this is the case we said n equal to 1, 2, 3 etc. So we said we have to find p naught. After all that we have written there for p n, ultimately all this rests on p naught. So we do not know what is p naught. So we had to find p naught. For that we use the total probability law or law of total probability, namely sum over all probabilities Pn, n equal to 0 to infinity is equal to 1. But why is this so? Because each one of them, that is each value of n can be 1 or 2 or 3. These events are mutually exclusive, and these are all mutually exclusive events, so that probability of the union of such mutually exclusive events will be equal to the sum of the individual probabilities. So, that is why we have this equation here, and this is a shear event. So, you have P of S, the sample space, equal to 1, and P naught when you sum up is given by this. We saw all this derivation earlier. So, we went on to start with the Markovian model, single server model, infinite capacity. So, where we assume the rates to be lambda and mu, constant rates, they do not depend on the state of the system. The mean inter-arrival time and inter-service times are respectively 1 by lambda, 1 by mu, and the same probability assumptions we made in the generalized Poisson queuing model carry through here, except that there we went on to use the state dependency rates. Here they are constants. So, we have written these probabilities as given here. 1 minus lambda h plus O of h gives the probability of no arrival in h units of time. Similarly, probability of no departure in h units of time is given by 1 minus mu h plus O of h, and with the respective probabilities of one arrival in h is given by lambda h plus O of h, that of one departure is given by mu h plus O of h. Similarly, we have the probabilities for more than one arrival in h units of time to be equal to O of h. Similarly, probability of more than one departure in h units of time is assumed to be O of h. Now, this leads us to the balance equations as here. These are the equations we are borrowing from the generalized Poisson queuing model, namely Mn 1 Gd infinity infinity. Further borrow the expressions for Pn and P naught from that model with the assumptions that lambda n equal to lambda, mu n equal to mu for all values of n. Always when it is arrivals, you can have n to start from 0, and if it is departure rates, the n should start from 1, because you talk of a departure only when there is one customer, minimum at least one customer in the system. So, remember that n always equal to 1, 2, 3 etc. for mu's, and lambdas, the arrival rates, n starts from 0 onwards. So, with the assumption that rho equal to lambda by mu, we have P naught equal to 1 minus rho, and P n we derived it to be rho power n into 1 minus rho. But because we had used the binomial series or the geometric series in these expressions, presently to find P naught we had used the geometric series. So, which requires rho to be less than 1 for convergence of that infinite series. So, we always assume that rho is less than 1, but we also went on to say that since rho which is equal to lambda by mu is less than 1, we end up with the quantity that lambda is less than mu. But what is the significance of this? Lambda is the arrival rate and mu is the departure rate. So, always, or the service rate. So, we always need to have the arrival rate to be less than the service rate, otherwise the queue will blow up. So, this also goes well with the theory. The assumption we have got is rho less than 1. So, next aspect is performance measures. So, here we have the performance measures, namely any arrival who comes into the system is worried about the waiting time in the system for the service to get done, be it the waiting time involved for the queue or with respect of the service. So, always we need to look into the calculate rather the performance measures based on the expected number in the system or expected waiting time in the system, similarly in the queue, in the service time. So, all these measures together we call them as the performance measures. So, let us take a short break at this stage. Welcome back after the break. So, we are into looking at the performance measures of the system. To start with, we have the notation to be used as the following, namely LS, which is given by expectation of n. This capital N written here denotes the number of customers in the system. So, n is a random variable, and once we say random variable, we need the probability of that. So, what is probability of n capital N taking the value small n? That is denoted by Pn. This n is always in the steady state. These performance measures that we are going to discuss now, they are aimed at the steady state. So, we bring in the probability of finding n customers in the steady state, that is Pn. So, we have here E of Ls equal to E of n, which is equal to sigma n equal to 0 to infinity n into Pn. We will just look into this derivation here. So, that is what I have written here, sigma n equal to 0 to infinity n into Pn. Now, what is the expression for Pn? We saw that, so I will rewrite this as sigma n equal to 0 to infinity n times Pn. Pn we got it as rho power n into 1 minus rho, P naught into rho power n. P naught we later on found it out as 1 minus rho. So, I am plugging in this expression for Pn here. Now, I will take this 1 minus rho out and write it as sigma n equal to 0 to infinity n times rho power n. Now, expand this, which can be written as 1 minus rho times open bracket, when n equal to 0 there is no contribution, when n equal to 1 we can write it as 1 into rho plus 2 into rho square plus 3 into rho cube and so on to infinity. Fine. Now, this is rewritten as 1 minus rho into, I always want to, the attempt is always made to be able to sum up the infinite series which is there with us under consideration. So, either we look into comparing this with a geometric series or if possible with the binomial series. So, here we rewrite this in that attempt. So, take that rho out, because all these series have the first term written as 1. So, this would be written as 1 plus, I have taken one rho out, remember. So, this is 1 plus 2 rho plus 3 into rho square and so on to infinity. Now, this is a familiar series, namely 1 minus rho into rho times, this can be written as 1 minus rho the whole power minus 2. So, what is that we are using here? So, the expression we have out here is Ls equal to 1 minus rho into rho we had taken out, and we have 1 minus rho, we had 1 plus 2 rho, right, plus 3 rho square and so on to infinity. This I said we can write it as 1 minus rho times 1 minus rho whole power minus 2. What is that we have used here? We have used here 1 minus x, the binomial series expansion 1 minus x whole power minus 2. This is written as 1 plus 2x plus 3x square plus so on to infinity. So, if you remember, 1 minus x whole power minus n is written as 1 plus nx plus n into n plus 1 by 2 into x square factorial and so on to infinity. So, when you put n equal to 1 here, 2 here, you get 1 plus 2x, which is what I have here, 2 into 2 plus 1, which is 3, 6 by 2, which is 3 x square and so on. So, we have used this binomial series expansion in order to sum up this series out here what we have, but this is valid because it is a binomial series. The series will converge only when rho is less than 1, but this excellently tallies with our steady state condition what we have. So, everything is absolutely perfect here. So, we can write Ls now is equal to 1 minus rho times 1 minus rho the whole power minus 2. So, cancel out 1 minus rho here, we get power minus 1. So, this gives us rho by 1 minus rho. So, Ls is obtained as rho by 1 minus rho provided your rho is less than 1. Fine. That is what is the expression in terms of rho for Ls. But if you want to write it in terms of lambdas and mu's, we can rewrite this as follows. So, you have to plug in Ls equal to lambda by mu divided by 1 minus lambda by mu. So, cancel out this mu here, we have this is equal to lambda by mu minus lambda. So, this is another expression for Ls. You have it in terms of rho as well as lambda and mu. So, this is what we have written here, that is Ls equal to rho by 1 minus rho. Now, the next performance measure would be that of LQ, namely the expected number in the queue or the system size, expected system size in the queue. What we found out now was the expected system size in the steady state. Now, it is the expected size in the queue, that is given as LQ, the notation, and we have it here written as E of NQ. NQ is the random variable denoting the number of customers present in the steady state in the queue. So, which is given by definition sigma n equal to 1 to infinity n minus 1 into Pn. You see the difference here. For Ls we wrote it as n into Pn, but for Q we are writing it as n minus 1 into Pn. Why is it so? You know that this is a single server system. If there are n customers in the system, then one customer would be with the server, and this is a single server system. So, how many would be there in the queue now? N minus 1 of them, and you are trying to find the expected number of customers in the queue. So, what is the size that can be possible? N minus 1 to start with. So, we have here this expression sigma n equal to 1 to infinity n minus 1 into Pn. Now, what is the Pn here? Pn is probability of finding n customers in the system in the steady state. So, we now plug in this expression for Pn, which is given by sigma n equal to 1 to infinity n minus 1, Pn is 1 minus rho into rho power n. So, as usual, take this 1 minus rho which is independent of the summation variable n. So, take that out, it is 1 minus rho into summation n equal to 1 to infinity n minus 1 into rho power n. So, plug in the values. So, this is again written as 1 minus rho into, when you put n equal to 1 there is no contribution because 0 into rho power 1 which is 0. So, the next term when n equal to 2 you get 1 into rho square plus when n equal to 3 it is 2 into rho cube and so on to infinity. Fine. As before I told you that always we try to take or put the first term as 1 to be able to compare it with a known series, either the geometric or the binomial, whichever is applicable here. So, we go on to write this as 1 minus rho times, take that rho square out, then we have 1 plus 2 rho plus next term would be say 3 rho square and so on to infinity. So, once again we write this sum as 1 minus rho into rho square into 1 minus rho power minus 2. So, what this gives us is rho square by 1 minus rho, because this 1 minus rho would get cancelled with this minus 2 and we will get minus 1 here. This gives us rho square by 1 minus rho. So, that is the expression we have for LQ. So, LQ is given by rho square by 1 minus rho. Once again we can try to put this as in terms of lambda and mu. So, what we have to do here is put rho equal to lambda by mu and substitute, cancel out the terms and write out the remaining expression in terms of lambda and mu. Why we need to write in LQ in terms of rho or lambda and mu? This is useful in problems. Depending on the information we have, we can plug in the expression suitably. At this stage we have found out the expressions for LS and LQ. Remaining expressions, what we need to find the other performance measures are in terms of the waiting time, namely the expected waiting time in the system for a customer and the expected waiting time for a customer in the queue. So, using the Little's formula, we do write these expressions as Ws. If you remember, in the initial lectures we had looked into the Little's formula. So, we have Ws equal to Ls by lambda, which is given by 1 by mu into 1 minus rho, or it is rho by 1 minus rho, and Wq is Lq by lambda. So, which is rho by mu into 1 minus rho. So, you can either write completely in terms of lambda and mu's or completely in terms of rho. Any method is correct. So, at this stage we will conclude this session, and as a summary, what we did today was we recalled the generalized Poisson queuing model derivation, and then we started with the Markovian queuing models. The first one is the single server model with no restriction on either the capacity of the system or the size of the source. And then we saw the derivation, or we derived assuming the rates to be constants for the arrival rates and the departure rates dependent on the state, but the rates for this model are lambda and mu respectively, which are constants. We plugged in these rates into the derivations of the obtained steady state probability Pn of the generalized queuing model, and we obtained the Pn and P naught, and which is appropriate for this model. So, which was Pn is rho power n into P naught, P naught was 1 minus rho, and then we saw the derivation of the performance measures of the system, namely the any newly arriving customer is expected to wait either in the queue or in the system, what is the service time the customer has to go through, and then expected waiting time, expected queue size, expected system size. All these performance measures are discussed in the steady state. So, we have at this stage obtained the expressions for all the performance measures for this single server Markovian queuing model. So, we will continue in the next lecture with more examples. Thank you.